Just to recap, NoSQL is a fairly lightweight approach, the way I look at it. It is an approach where we don't burden ourselves with a predefined schema in place. We can introduce a schema at a later time if we wanted to, but to begin with, we don't have to take the burden of a schema. It becomes a lot easier to evolve the application on the database by introducing new kinds of data and new kinds of relationship as we would like to. What are the kind of data that we would normally store in a NoSQL database? The type of data we would store typically are called as application data. These are data that often are not shared across multiple different applications, but are really for concurrency across multiple users using the application. Now, the benefit, or you could say, why is it that we want to really focus on a multi-user but not multi-application? And the reason is the time when multiple applications have to interact with the data, you would have to then be meaningfully able to communicate the structure of the data to these different applications, and herein we would need the schema. But if you have only one application predominantly using this particular database, then the schema is not as critical to use, and so multi-user concurrency is the focus in this case. Now, it turns out there is no one NoSQL. There are quite a number of different NoSQL databases. But at the very high level, the NoSQL databases can be categorized into two different flavors. One is called an aggregate-oriented databases, and the other is mainly relationship-oriented databases. The aggregate-oriented databases really focus on aggregates or collections of data. On the other hand, if you look at the database that focuses on relationship, they predominantly are focused on how objects or entities are related to each other. So in typical settings like social networking, for example, where you're really interested in mining through the relationship of different people, you would more than likely be using a relationship-oriented database like Neo4j, for example. Whereas if you're really interested in the traditional data where we are mostly interested in drilling down into a certain entity and having more information about it, you're most likely going to be using an aggregate-oriented database. But what does this word aggregate-oriented really mean? Well, what it really means in the case of aggregate is that you have a hierarchy of objects. Maybe you're interested in storing information about employees, and you may have an employee's first name, a last name, possibly a phone number, an email address, and then, of course, you would want to have their own address properties. And then when you have the address, you may have things like their mailing address and shipping address and address for tax purposes, where do you communicate, and you may be interested in some of those details. And then you may be interested in details like what projects this person is working on. You may be interested in other details pertinent to this employee. Maybe you want to know about the benefits this employee can have, maybe what kind of insurance this person can have. Maybe then you are interested in the family members this person can have. So notice how you're drilling into more and more and more detail about one particular person or an employee, and that is really where the word aggregate really comes from. So aggregation of data is what we are really interested in, an aggregate-oriented database, and that's what we predominantly are focusing on in this particular case. Now, focusing only on the aggregate-oriented databases, we can think about these kinds of databases to, again, fall into a category of about 3 more different subdivisions, if you will. So if you really look at the lay of the landscape at the very top, at the NoSQL level, you can say there is this one box called NoSQL. Under that, there are 2 boxes. One of them is the relationship-oriented, and the other is the aggregate-oriented. The relationship-oriented is fairly flat. Once you go to the relationship, you got relationship-oriented. But on the other side, the aggregate-oriented, you have 3 more things dividing from there. So you can think about there's one box, and you have 2 boxes, and then this box here contains 3 other boxes below it. And those 3 boxes predominantly are depending on how or to what granularity you store the information in the database. So if you look at this aggregate-oriented databases, the very simple one really starts with a simple key value pair. So you can think of this as a little bit more glorified hash map, where you have a hash map. And what is typically a hash map contains? If you program in Java, for example, you used a hash map. In a case of C#, you probably have used a dictionary. If you're programmed in Ruby, you have used the hashes as well. If you're programmed in other languages, you've used similar structures. These are really key value pairs that are associative maps, as we normally call them. That's what we store, right? So we have these keys, and then we have the values associated with them. So think of this as a little bit more glorified implementation of a key value store. That is one of those implementations we work with. And we can go a step further beyond that, and we can say we could also have a document-based databases. And the word document here is, as we may want to think about the word document as XML document or JSON document and stuff like that. That's what the word document really means in this context. And so the database may go a step further and say, well, I could have a key and a value pair, but the value may not be a simple object. It could be a document. And so you could store that. But you could go a step further from that, and you could also have what's called a column family databases. And in the case of a column family databases, then this database goes to the next level where you have a key which kind of works like a primary key, and then may end up having a family of columns associated with that particular key. So those are the options. We'll drill down and talk about each one of these a little bit later. But essentially, one of the reasons to choose these kinds of databases is we really want to be able to support very high availability and also be able to provide scalability. Now, the way to provide this is to provide clustering based on the aggregate. So how does this really work? So let's understand first the essence of really the reasons to use this. So if you're going to have one database sitting there and serving multiple different requests that's coming in the traditional approach that worked really well when the number of requests were in thousands and tens of thousands, even hundreds of thousands. But it doesn't really make sense to use that approach when your requests end up being in millions of requests. Now, granted, not every application in the world is going to require those kinds of millions of instructions, accesses per second, but there are several applications that do. And those applications predominantly cannot survive with the relational database models. Now, having said that, I would ask the question, well, if I don't get millions of requests per second, does that mean I really don't need to use any of these databases? Should I walk away from this room? The answer is no. There's a good reason to use these databases still. And the reason is, if you do realize, even if you don't have a big data, as they call it, as a big data, where you have a lot of these interactions that happen per second, you may say, well, my application data, even though it may not have that high volume or frequency, fits into that category of the data. And why should I take that extra effort, time and effort, and the complexity that I have to use in a relational database? Can I not just deal with some of these databases and have something come to production very quickly without spending all those time and effort? Now, one of the things that I care about a lot is, to me, software development is series of light bulb moments, right? And how many times are you sitting at work, you're working on something, and suddenly a light bulb comes in your head and it says, oh, wouldn't this be so cool if we can do this? And then your face brightens up and your muscles tighten up and you're all excited about it. That would be a great idea. I want to implement it. And the next thing you realize is to implement it, you got to set up a stupid database, define schema, and you think about all those 20 things you do, and that just sucks the life out of you. And then you're like, let me go back to editing this XML file again, right? I'm not going to be doing that. So what you want to do is you want to be quickly able to put something together and try it, and then go get the feedback and say, hey, does this make sense? Do we want to do something like this? Would there be a market for something like this? Can we even entertain this thought? And you don't want the burden of doing silly things to get that into that mode. And so you want really to get to that point with minimum effort as much as you can. And of course, you don't want to really do things that are not necessary to get that into production following the traditional approaches we are used to. So in order to do this, we really want to be able to use lightweight databases. In terms of clustering the aggregation, though, when you do have those frequency of data we talked about, how do we really provide that kind of frequency of support? So imagine a request comes in for a data, and if you're going to have the data on one single machine, that particular database simply cannot give you the throughput. So we have to really start expanding it. Well, it turns out there are two kinds of ways to scale. One is vertical scaling and the other is horizontal scaling. Vertical scaling is to throw more hardware at it, to throw more memory at it, to throw more CPU processing power at it, and then you're saying make it bigger and better. Well, it turns out the more CPUs that you add, the more power you add, the more memory you add, the more it costs to do it, but it doesn't give you the bandwidth. Why? Because you're still increasing more threads, and there's only so much more threads you can add to a particular processor. The amount of memory still restricts the number of threads you can have on a processor. So vertical scaling has serious limitations. Horizontal scaling, as it turns out, is relatively cheap. Because if you have an option of doubling the processor capability versus having two processors with the same capability as they had before, you may get really more throughput doing that. In fact, you can expand out even better. So the real idea here is the hardware is so relatively cheap that you can actually have a lot of these available to you. And in fact, that's how the clouds are really created. Clouds have a lot of little processors that can come into life and go. In fact, this is even better. Because what you can then do is you can say, hey, depending on the load I have available, if my load time is really not much, or if the load is relatively minimal, I want fewer nodes to be up and active right now, but suddenly there's a surge and the load increases. I want nodes to come to life at the time, serve those requests, and when the load goes down, the service goes down, which has a definite economic impact for your business. After all, if you're making more money, you don't mind spending a little bit more money on the hardware. If you're not making money during a certain amount of time, you would rather not waste the money on the hardware sitting there ideally. So with dynamically configurable cloud computing today, it only makes more sense to have these kinds of systems come to life and die away, and we can configure these to say, here is the number of nodes I want based on the peak hours. I want them to come into existence and go away. So if you're going to do some of these things, what we really want to do is to be able to have to distribute these across different nodes. Now, given this, but how do we really manage to do it? Well, let's take a little example here. Let's assume, just for the sake of the discussion, we have different nodes, and let's say that these segments are different nodes, and we could say, for example, and what's your name, sir? Double's node is going to be on this machine right here, right? So we're going to put it on this machine, and all his data and details about the pets he has at his house, their names and what kind of pets they are, all of them are going to be kept on this particular node right here, right? On this one is, what's your name, sir? Deepak's information is right here. Now, but how do I know where is Double's data and where is Deepak's data, right? And I could have millions and more data on the system. Well, there are a couple of different ways we could do this. One way is when I get the request for Double's data, I could use a very simple bucket hashing, right? Just like how hash maps work. What do hash maps do? They take the key and they do a hash on it. That's what they call hash map. They do a hash algorithm on it, and they find the bucket in which this particular data is going to reside. And so the node over here is based on the hashing of his ID, and the bucket would lead me to this particular machine versus US would go to this machine. That's one way to do it. The other way to do is not to use these hash algorithms, but instead we could do a range operations. For example, a range of keys from this value to this value is going to be on this machine, and this is kind of like a trivial bucketing, right? Where you use a range as the bucket itself, and you can put these across. And that is one way to do it. Well, of course, this really gives us the ability to do scaling, but there is one problem, though, that this machine may go down, in which case a number of our users are not going to be able to use the system while the others are still able to use it. That's great. At least some people are able to use it. But if we can shard it or replicate it across machines, so this is the primary server for the Double's data, but we're going to replicate it over here on this machine. Likewise, this is going to be Deepak's data, but we're going to replicate it on this machine. So if one of these machines go down, we can still get to the data from another machine, and we want to have these replications or sharding on top of this as well. So these are some of the common techniques that are being used with most of the aggregate databases. But that leads to one concern, obviously, here. All of Double's data is on this machine, all of Deepak's data is on this machine, which means that when you're making a request, it is going to provide consistency only across one of these machines in which the data is. So typically these databases provide what are called document level consistency. So as long as you're able to update the data within a document, then you have consistency of the data within the document. But if you're going to be updating data across two different documents, and maybe I'm interested in updating Dhaval's data and Deepak's data at the same time, I can be guaranteed consistency across those, and that is something that these normally end up providing. So we talked just a little bit about these three types of databases and the clustering need, but we want to be able to navigate easily and get the data, but it's at the same time generally hard to perform ad hoc queries. For example, again, this is where databases try to set them apart from one another, but based on the concept in general, you could say, I could say, hey, I want to get some information about Dhaval. I want to know how many pets he has. I want to know how many of his pets are, blue in color versus white in color. I could ask some of these query details because all of that resides over here. But if I want to really take this query and say, how many people here have a certain type of pet, well, that would have to go across different nodes in the cluster, and that means I got to send queries to multiple machines to do that, and it's really not geared automatically towards it unless a database specifically says, we will provide this at a certain, a time complexity cost as well. So we will have to then visit the nodes and get it. So what about the ACID transaction? So these provide ACID transactions within the aggregates as we talked about. So atomicity, consistency, isolation, and durability is available as long as you update data within a document, and across documents these often are not provided. Now let's talk about each of these specific databases and see what they provide for us. So let's get to the key value databases. Like I said, these are very basic set of operations on a hash map kind of a solution where you have a key and a value. Now, what is the value? Well, the databases basically say the values are merely a black box, right? They don't care about what these values are. So these could be pagers, these could be binary objects. They simply don't care. They just treat them as a black box. You give a key, and you can give a value, they store it, and then you give a key, and they can give you the value back. So this is like you go to a safe deposit box, and you say, here's the money, and I want to put this in here, and they shouldn't care what you put in there unless you leave a dead fish in there. They can quickly find out, and they keep it in the safe box, and of course you can go back and give your credentials, and they can return your stuff back to you. So you can think of this as a mere store. Given a key, you're going to keep the value, and given the key again, you can get back the value back from these databases. So they are a little bit more than a glorified hash map in that sense. So you can store whatever you want to store, but how does the query really happen? The query happens based on the key alone. You give a key, either you get the value or you don't have a value to get, and that's all you pretty much do with these kinds of data stores. Now, given this, they can store basically binary large objects. They could store, strings, whatever. It really doesn't matter. So the access is only based on the keys, and buckets of data are provided like we talked about. Some implementations, of course, break away from these limitations. Now, the question is, what kind of data would we typically store in these? And I mentioned that we normally use these for application data and not enterprise data. So these application data really are data that usually one single application, you could have multiple instances of the same application, that's perfectly fine, but this is one single application that you are really, it's a cohesive set of application that you're using that is interested in this data. And you're not really interested in sharing this particular data across the enterprise. This is pretty much for this particular application. Let's take a look at some of the examples of the databases and the types of data we would store in this. So the typical databases that provide this are things like Berkeley DB, DynaDB, and HamsterDB, and Project Voldemort, Memcache DB, Redis and React. These kinds of databases are really focused on, again, some of these can give you extended capabilities, but these predominantly support this key value kind of a store. Now, what kind of data would you typically store in these particular databases? Well, you would store a session data. If you really think about a session data, what is really a session data? Well, you have a user's kind of credential on your hand, and you are sticking stuff into the session data. What would you store in a session data? Well, that's entirely up to you. You may store a user's ID information. You may store maybe an email address of the user. Maybe you want to store some useful cached information to speed up the query the next time the query comes in. You may want to keep track of where the user is logged in from. You may want to keep track of a certain temporary credential about the user, what have you. That's your business, your application's business, what you store in that session data. So typically you would store in the session data some of these things, and you could store the session data in these databases. A shopping cart is another good example of this. What does a shopping cart have? Well, that's your application's details again. You may decide to say, I'm going to store the reference number to the item that you are purchasing, maybe the number of quantities of the item you're purchasing. Maybe I want to even store the price that I promised for you at the purchase time when you're adding it to the shopping cart. These kinds of details I may store in the shopping cart, and you may be building your shopping cart for the next several minutes to several days, right? If you're like me, your shopping cart is probably very, very long persistent. Sometimes I would add things to my shopping cart. Somebody would mention a book name, and rather than writing it down, I would go to Amazon and say add to my wish list or my shopping cart, and it's just waiting for me in there. The other day somebody mentioned a book and said, have you read this book? I said, I'm sorry, I've not read that book, and I immediately added to the shopping cart. But 3 weeks goes by, I totally forgot about this book, and the guy comes back and meets me in another place. He says, hey, the book I mentioned to you, did you buy the book? And I said, I'm sorry, I really did not get a chance to buy it. And he said, good, I'm glad you didn't buy it because I bought it for you. This is the time when you wish that it's like, yes, I'm glad I didn't buy the book. Well, so I got the book for free at the time, of course, and of course, promptly I went and removed it from my shopping cart, right? So that is purely an application data that you maintain for a while, and then you can throw it away, you can complete it, and when you complete it, of course, you still throw it away, but that becomes transformed into potential enterprise data because now it's got to go through the order processing system so that it can be processed at that point and what have you. Similarly, user profiles. When would you store a user profile? Typically, I would use a user profile to be stored on a single machine, but what's going on today is something very fascinating. I typically use 2 or 3 devices exactly at the same time, looking at exactly the same data in the same application. For example, I most likely am looking at my airline reservation. I travel about 270,000 miles a year, which means I spend a lot of time on an airline website. So I will be on my laptop looking at my airline reservation. While I'm looking at it, there is actually a better way to access this using the mobile device because they have a little bit of a better interface, and I'll be using my mobile device at the same time, working through it. But then when it comes to certain other features, the desktop version actually is a little bit better than this one, and I'll just drop my device and go back and start using it there. And you may want to have this opportunity to use multiple different devices. But there are some preferences that I have set, a certain time zone possibly where I am, or other preferences I may be able to set. But you want to keep this in track of who the user is. But that, again, is very specific to this application. And it's something you could even wipe out after a while and then reset it. So user profiles could be, or preferences could be stored in these also. So these are the kind of data that you want to store. But in each one of these, notice the reality of this. It is usually an all or nothing proposition in these kinds of data. You give a little key, and you get the data, and the application consumes this entire data, may regenerate a set of values, and it's going to store that back. Very rarely would the application be interested in querying into these data, and so that the fact that it's being used as a blob or a little a value object is perfectly okay in these situations. It seems to work most of the time for the purpose intended. So those are the key value databases, and we saw a few examples of those databases here. Now, on the other hand, we could also use a document database. Document databases typically are the things that store a document, and the word document here, as I mentioned, is like an XML document or a JSON document or a binary string object documents and what have you, and you may be storing these kinds of documents. Now, the purpose of storing a document is not to say you can store those documents, because if all you claim is that you're storing those documents, it is nothing but the key value database, because you're storing the document, you're giving back the document. What good is that? But the real benefit of these databases is that you can go to these databases and you can query these databases based on certain values within this document. For example, you may go to the database and give an XPath query and say, hey, go find out among all this data in the database, which of the values or the entities in the database have this particular property from the XPath query, or you can examine based on partial data within the database and fits those data. And the benefit in this case is, of course, you can make queries based on this partial data that is within the document itself. So imagine you have a fairly large XML document you have stored, and you may say, given all these data, I want to only query for this document which has this information. Do be a bit careful, though, when you do perform these queries, you need to make sure that you're not really reaching out to across the document kind of queries. This is still within the document that you need to be careful about, because, again, you can have distribution across machines, and you're not getting the full set of data if you're not being very careful about it, or the database actually supports queries across multiple nodes. So basically, these are structured around the aggregates and the types of the data. But the beauty of this is they have much more flexibility in terms of query and access they provide, much more than the key value databases do. Because all that the key value databases do is you can park this object and come back and get the whole object, whereas in this case you can go ahead and query for parts of the document also. So parts of the document can be queried, parts of the document can be updated, and that gives you either a full access to things, or you can go get a sub-content as well. You could also have indexes based on the contents of the document, and so you normally work with IDs and the document values itself. So what kind of databases support this kind of approach? Well, the databases that pretty much support these kinds of storage or a document database are CouchDB, Terrastore, MongoDB, OAMDB, and RavenDB. Now, what kind of data would you store in these kinds of databases? Well, the word document, the word hierarchy, and there are certain types of data that fits into this really well. One of them is logging. And if you really think about logging itself, you want to typically log certain conditions. You may have a little information about what you're logging, the time you're doing this logging, the error conditions that may have, exception details that may be there, or other information like how much memory you had at the time, what was the session, who was the interactive user. If you notice, all these kinds of data again fall into this hierarchical structure: machine details, user details, system details, time of the information. All these kinds of information could be stored in a log. Now, while this is really useful, there are times when you want to query across the logs as well. So if there's an incident report, for example, and you say, hey, something went wrong and we want to know if there's a systematic failure related to this, you may go to the log file and query about a certain pattern and try to find out these details. So querying inside the document becomes necessary. Another information that fits really well into this category is the blogs. If you really think about blogs themselves, notice how hierarchical blog structures are. So typically what do you have? A person is blogging, so each blog is the first level of hierarchy. Within a blog itself, you have a title for the blog, you have a set of keywords for the blog typically, and maybe a subtitle for the blog. And then you have the main content of the blog. The content itself may have paragraphs and sections and subparagraphs and subsections. And then you may have a comment section. And then comes a comment for a comment, and then a comment which has a comment, which in turn has a comment, depending on how powerful. Time normalizing and normalizing, and by the time you have something working, the need for that would just disappear, right? So it's really not something that fits nicely into this hierarchical structure. As relational database is nicely normalized, you don't want that kind of normalization. You really want a true hierarchical representation, and you don't have that capability really given to you in a relational database, whereas a database like this fits extremely well because you can just come to a tree structure, can add more nodes to a tree structure. A leaf node can suddenly become a node and can have its own children trees, and then it can continue further with this very easily compared to what a relational database provides normally. So again, blogs kind of fit really well into this. Content management systems also fit really well into this as well because they follow exactly the same kind of structure that you got, again, topics, you got references. You also have links to other things also, which is another thing we have to keep in mind, because oftentimes when you have a content or if you have a blog, you want to refer to other related articles and content as well. Again, this is very concerns, something that is very nicely hierarchical but doesn't fit really well into a relational database. So those kinds of data fit in really well into a document database also compared to a relational database. So that is the second type of these databases that are available. On the other hand, we could also go further into a column family database. Now the column family databases say that they would store a group of columns. So what does that mean? You have a row of data, and you have a primary key for the data, and you have columns that contains the values. You may say, wait a second, doesn't that sound a lot like something we're trying to avoid in the first place? If they're going to have row columns, after all, isn't that what relational database is? Well, there is a big difference, however. The difference is, let's say for a minute, that we have a relational database. What a relational database is all about? The relational database is all about conformance, right? You got to be a cookie cutter. Everything looks the same. And that's like being back in elementary school. Remember that time when you had to wear this uniform and you had to wear a tie? Boy, I hated those days because everyone looked like every other kid, right? And one day the teacher comes and says, your hair is a bit longer, right? So that's like everybody looks the same. What fun is that, right? We're all different. That's where the real fun is. So you have this conformance model going. Well, let's look at an example for a minute. Let's say I want to store information in a relational database. Then what do? Well, I'm going to store information about people. Well, I'm going to have a first name and a last name. Guess what? Everybody has a first name and last name. Great, I define columns in there. Then I'm going to say I'm going to store maybe an email address. I throw in an email address. So we got some of those details so far. Now maybe I want to store some other information. So I'm going to ask you, for example, hey, what sport do you like? He's like, come on, how would you even ask that question? He's like offended. Did you see that? You should have seen him from here. He's like, duh, cricket, right? I thought cricket was not a sport. They said it's a religion, right? I asked you for a sport, right? I didn't ask you for a religion. Yeah, it's like cricket. I come through the airport the other day, and like there was nobody. I'm like, dude, flight. And I looked at this, where are you from? There's match going on. We fly you somewhere, right? You remember this Tom Hanks movie? He was stuck in the airport for several days. That was me. Because there was cricket going on, right? I know this, so I'm feeling, right? So yeah, cricket. So what do? I define a sports column, and I'm going to store cricket in it, right? And I'm going to ask her, do you like cricket? Not much. You want to move that sits over there, right? These guys are not going to let you sit here anymore, right? But she said not much. She said don't like it, right? She's very cautious. But now, in the sports column, I'm going to be null for her. She's got to be conformant, right? She says, I don't want a sport. Maybe I like music really well. I'm sorry, but you need to have a sports column. Our sport is DB null, right? How sad that is, right? To have a DB null as a column. Well, that is kind of the emphasis we have, is that we have conformance. So why? Because then we can query, and there's always this property. We can create a Pojo, and then we can go to that and say, get me the sport, and of course, DB null is a valid value. We got to deal with it. Well, none of that. Every single row can have its own set of values, right? So he says, you know what, I'm going to have cricket as a sport, no worries, cricket as a sport. She says, I actually like, music, and I got a genre of the music listed over there, that's perfectly fine. And he says, hey, look at me, I love music, I like sport, well, I can have both of that for you as well. So every single row can have any number of columns. You're not in this conformance model, and so this is different from the relational data in that you can have as many columns or as few columns as you like, and that is perfectly fine. You can have that. So you can have these kinds of columns listed, and there are two kinds of aggregation here, two levels of aggregation. You can simply have a key to value pair, or you can also have a key to value to the column of data, which could be a little bit more complex set of data as well. So the columns are grouped together as these families of columns. If you say, for example, here are some group of objects, and they carry with them a common set of properties, and why do I want to only deal with differences? In other words, I have the best of both worlds.